So the linearization theorem at first looks kind of odd, and we'll give it some insight later on, but let's see how it works first. So let y naught, so that's kind of a vector, be an equilibrium point. So just define the equilibrium point y naught to be the equilibrium point, the ordered pair x0, y0. So it's just some point for the nonlinear system. Dx dt equals f of xy, dy dt equals g of xy. Its Jacobian matrix, this is a definition, Jacobian matrix at the equilibrium point is the matrix with the partial derivatives. Now we're calling dx dt f of xy, so when we say df dx, we're saying take the derivative of this function with respect to x, take over here the derivative of that same function with respect to y. So this whole first row represents dx dt, so they're all going to relate to the original nonlinear dx dt. When we take these derivatives and evaluate them at the equilibrium point, what we're going to get is a set of constants that will represent a matrix full of 4 constants looking like a linear system. In the second row, that relates to dy dt, so that's going to be the derivative of g with respect to x, and the derivative of g with respect to y, and then we'll plug in the equilibrium point in question, and what that will give us is the 4 coefficients that we'll need to produce the linearized system. So basically, we're going to take our nonlinear system, we're going to reduce it to a linear system. So notice this looks like AY, but we call it JY. We do that because we don't want to make it seem as though our original system was linear to begin with. So we're basically linearizing it by computing this Jacobian matrix. We'll give a little bit of insight into this. It turns out it's pretty intuitive, but let's not do it now. Now this does have some restrictions. If the determinant of J is not 0, so this is the valid linearization as long as 2 things hold. The determinant of J is not 0. That is, this is the notational way to write it. And the eigenvalues of J are not purely imaginary. So for example, purely imaginary would be if I wrote 3i. But something that is not purely imaginary would be something like 2 plus 3i. So here you have a real part, a non-zero real part, and a imaginary part. We're not going to get into why this is specifically true here, but if these 2 conditions hold, then the solution curves of the nonlinear system near that equilibrium point behave in the same qualitative way as the solution curves of the linear system. We've already seen that that is the case from these 4 phase planes when we looked very close to our equilibrium points. Now we have a way of actually computing that linearized matrix. Once we have that linearized matrix, we can compute its eigenvalues, and we know just based on the eigenvalues whether that point will behave like a sink, source, spiral sink, spiral source, center, or saddle point. So first of all, when you compute the determinant of a matrix, so when you have 4 values like this, it's the product of the diagonals from top left to bottom right. So you see there's A times D, minus the product of the diagonals from bottom left to top right, BC. So you have to check, make sure that's not equal to 0. As long as it's not, you're all set. The second thing that we need to just ensure that is that the eigenvalues are not purely imaginary. And that's when after we have verified that the determinant is not 0, that only at that point can we go and investigate and look at the eigenvalues themselves. So if you find out that the determinant is 0, you stop there. This theorem is not going to be useful. At that point, all you can really do is kind of do this type of analysis where you zoom in, if that is at all possible. So note 1, the theorem is quite vague in what same qualitative way means. The implication is that the behavior of the linearized system is similar to, but not necessarily identical to, the non-linearized system for initial conditions near the equilibrium point. And then the second kind of question that we want to ask is, what kind of equilibrium is disqualified by this theorem? Well, if you get a purely imaginary eigenvalue, that means that you're going to have 0 plus or minus hi. And if G is 0, then you get a center. If G equals 0, the equilibrium point is a center. Now, just because you get a 0 real part doesn't mean it can't be a center. It just means that if you get a 0 real part, the theorem cannot promise you anything.